Today we discuss the rank, nullity and the fundamental spaces of a matrix. So in this section we discuss the dimensions of the null space, the row space and the column space of the coefficient matrix of a given system of equations. So these dimensions are respectively the nullity, rank, etc. Theorem 1. The row space and column space of a matrix A have the same dimensions. That is, dimension of the row space and dimension of the column space of a given matrix are the same. Proof is a simple proof. We know that elementary row operations do not change the dimension of the row space or the column space of a given matrix. Even though the elementary row operations changes the row space, the column space and row space, they do not change the dimension of the row or column spaces. Thus, if R is the row echelon form of A, then dimension of row space of A equal to dimension of row space of R, and dimension of column space of A equal to dimension of column space of R. So it is enough to prove that dimension of row space of R equal to dimension of column space of R. Now, the row vectors with leading ones, so they form a basis for the row space of R, and we know that the dimension of the row space is nothing but it is a number of rows with leading ones, and the vectors which forms a basis for the column space is the rows corresponding to is the columns corresponding to the rows with leading ones, and the column vectors with the leading ones of the row vectors form a basis for the column space of R. Thus, the dimension of row space of R is the number of rows with the leading ones, and the dimension of the column space of R is again the number of rows with leading ones. Here, these two are the same. Thus, dimension of row space of R equal to dimension of column space of R. Hence, dimension of row space of A equal to dimension of column space of A. We have definitions of rank and nullity in the next section. So, above we stated that dimension of row space of A equal to dimension of column space of A. So, these two are a common number. Therefore, this common number is defined as the rank of A. So, the dimension of the row space or the column space of A is called the rank of A, denoted by rank in bracket A. And the dimension of the null space is called the nullity of A, denoted by nullity bracket A. Second theorem, which is the dimension theorem for matrices, which states that if A is a matrix with n columns, then rank A plus nullity A equal to n, the number of columns of A. So proof goes like this. A is a matrix of n columns. So rank of A equal to dimension of row space of A, and nullity of A is equal to dimension of null space of A. So the null space of A is nothing but the solution space of Ax equal to 0. Therefore, nullity of A equal to dimension of the solution space of Ax equal to 0. Since A has n columns, Ax equal to 0 has n unknowns. And this system being homogeneous has either a unique solution or it has infinite number of solutions. So if it has a unique solution, then there are no free variables, and if there is infinitely many solutions, then there is at least one free variable. So in the first case, when there is a unique solution, all the variables are leading variables, no free variables. In the second case, there is at least one free variable. So in any case, the number of leading variables plus number of free variables is equal to n, which is the number of unknowns. But leading variables corresponding to the leading ones in any row echelon form of A, and number of leading ones is the rank of A. Therefore, the number of leading variables is nothing but the rank of A. The number of free variables in the general solution of Ax equal to 0 is the number of parameters in that solution, and it is nothing but the dimension of the solution space of Ax equal to 0, which is nothing but the nullity of A. Therefore, number of free variables is equal to the number of parameters, which is nothing but the nullity of A. So, when applying these two or substituting these two in the equation star, we have the proof of the theorem. Third theorem is, if A is an m-by-n matrix, then rank A equal to number of leading variables in the general solution of Ax equal to 0, and nullity of A equal to number of parameters in the general solution of Ax equal to 0. And it is nothing but it is a restatement of the, or it is some statement which is followed from the previous theorem. Theorem 4, if Ax equal to B is consistent linear system with m equations of n unknowns, and if the rank of A is equal to R, then the general solution of the system contains n minus R parameters. Okay, so the number of parameters in a system of m equations where the rank of the coefficient matrix is R is n minus R. So proof is like this: since Ax equal to B is consistent, its general solution is the sum of its particular solution and the general solution of the corresponding homogeneous system Ax equal to 0. This is already proved in the previous class. But the particular solution has no parameters, and therefore the number of parameters in the general solution of Ax equal to B is nothing but is the number of parameters in the general solution of Ax equal to 0, and it is nothing but it is a nullity of A. Hence, by the dimension theorem for matrices, we have number of parameters in the general solution of Ax equal to B is equal to nullity of A, which is equal to number of columns minus rank of A, and that is equal to n minus R. And this is followed from the dimension theorem. Okay, so let us discuss an example. Find the rank and nullity of the given matrix and verify the dimension theorem. So you can see that by row reduction, the given matrix is row echelon form is this, where there are 3 leading ones in the rows. So there are 3 non-zero rows, and therefore rank of A is equal to 3. And nullity of A equal to number of parameters in the general solution of Ax equal to 0. So solving Ax equal to 0, you can see that there are 2 free variables, and therefore the nullity equal to 2. So you can see that rank plus nullity equal to 5, which is nothing but the number of columns of M. So we have verified the dimension theorem for matrices. Second example is, what is the maximum possible rank of an m by n matrix? So there are m rows and n columns, and we know that the number of the dimension of the row space of A or the column space of A is the rank of A. So the dimension of the row space of A is less than or equal to n, because row space of A is a subspace of Rn and column space of A is a subspace of Rn. So dimension of Rn is n and dimension of Rm is m. Dimension of Rn is n, dimension of Rm is m. So any subspace of Rn is of dimension less than or equal to n, and any subspace of Rm is of dimension less than or equal to m. Therefore, dimension of row space of A, which is equal to dimension of column space of A, and which is the rank of A, is less than or equal to both m and n, which means it is always less than or equal to the minimum of m and n. Third example has 2 parts. A is, find the number of parameters in the general solution of Ax equal to 0 if A is a 5 by 7 matrix of rank 3. And B part is, find the rank of a 6 by 5 matrix A for which Ax equal to 0 has a 2-dimensional solution space. So for the first part, we know that number of parameters in the general solution of Ax equal to 0 is number of parameters is equal to number of columns minus rank of the matrix, and it is 7 minus 3 equal to 4. And for the B part, given solution space is of dimension 2, which means the nullity is 2. Therefore, by dimension theorem for matrices, rank plus nullity equal to number of columns. Therefore, rank equal to number of columns minus nullity, that is 5 minus 2 equal to 3. Now we move on to the fundamental spaces of a matrix. So there are certain spaces associated with a given matrix, especially namely the row space of A, column space of A, the null space of A, the null space of A transpose, and of course the row space of A transpose and the column space of A transpose. But in A transpose, the rows of A are interchanged to the columns of A transpose. So the columns and rows are interchanged. Therefore, row space of A equal to column space of A transpose, and column space of A equal to row space of A transpose. Therefore, those two are same. So there are 4 distinct spaces associated with a given matrix A and its transpose A transpose, namely the row space of A, the column space of A, the null space of A, and the null space of A transpose. These 4 distinct spaces associated with A and A transpose are known as the fundamental spaces of the matrix A. There is a theorem: for any matrix A, rank of A and rank of A transpose are the same. So we know that rows of A equal to columns of A transpose and columns of A equal to rows of A transpose. Therefore, rank of A is equal to dimension of row space of A, which is nothing but the dimension of column space of A transpose, which is the rank of A transpose. So remark, let A be an n by n matrix, then A transpose is an n by n matrix, and therefore rank A transpose plus nullity A transpose is equal to m. But rank A transpose is equal to rank A, therefore rank A plus nullity A transpose is equal to m. Thus, if rank A equal to R, then the dimensions of all the 4 fundamental spaces of A are given by dimension of row space of R, that is rank of A equal to R, dimension of column space of column space of A, which is again rank of A, is R, dimension of null space of A, which is the nullity of A, is n minus R, and dimension of null space of A transpose, which is the nullity of A transpose, is m minus R. Now let us establish a geometrical link between the fundamental spaces. So the above formulae, we have 4 formulae. They give an algebraic relationship between the size of the matrix and the dimensions of its fundamental spaces. So in the following section, we established a geometrical relationship between the fundamental spaces themselves. So we require certain definitions. Let u equal to u1, u2, etc. un, and v equal to v1, v2, etc. vn are vectors in Rn. Then the dot product or the Euclidean inner product of u and v is denoted by u dot v and is defined as u dot v is equal to u1 v1 plus u2 v2 plus etc. plus un vn, which is nothing but the sum of the coordinate wise products of the components of u and v. So u dot v is sigma ui vi, I from 1 to n. This is the dot product or the Euclidean inner product. So you can compare this with the dot product which you have studied in the vectors. You have already studied vectors where you defined dot product also. The same dot product extended to vector spaces. The second definition: 2 non-zero vectors u and v in Rn are said to be orthogonal or perpendicular if their dot product u dot v is equal to 0. So any 2 vectors whose dot product is 0 are orthogonal or perpendicular. Again you compare with the vectors you have studied. We agree that 0 vector is orthogonal to every vector in Rn. We have certain remarks. In terms of the definitions, the linear equation a1x1 plus a2x2 plus etc. plus anxn equal to 0 can be written as a dot x equal to 0, where a is the vector a1, a2, etc. an, and x is the vector x1, x2, etc. xn, both subsets of, both elements of Rn. As a second remark, let A is an M-by-N matrix Aij. Then let us consider the homogeneous linear system Ax equal to 0 in n unknowns. So that will be the first row of A into x1, x2, etc. xn equal to 0. And the second equation will be second row of A into x1, x2, etc. xn equal to 0, etc. etc. Nth row of A into x1, x2, etc. xn is equal to 0. So if r1, r2, etc. are the row vectors of A, then this system is nothing but r1 dot x is equal to 0, r2 dot x equal to 0, etc. rm dot x equal to 0. So in dot product we can express like this, and this means r1 dot x equal to 0 means r1 and x are perpendicular or orthogonal to each other. R2 and x are orthogonal to each other, etc. Rm and x is equal to 0 implies Rm and x are orthogonal to each other. This means every solution vector of Ax equal to 0 is orthogonal to every row vector of the coefficient matrix. That means if x is a solution to the given system, then x will be orthogonal to every row vector of the given matrix A, which is the coefficient matrix of the space, of the system. Sixth theorem is, if A is an m-by-n matrix, then the solution set of the homogeneous linear system Ax equal to 0 consists of all vectors in Rn that are orthogonal to every vector of A. And this is nothing but the proof is the second remark given above. Another definition is orthogonal complement. Let W be a subspace of Rn. Then the set of all vectors in Rn that are orthogonal to every vector in W is called the orthogonal complement of W. So any vector which is orthogonal to every vector of W is in the orthogonal complement of W. So that means a vector x belongs to the orthogonal complement if x is orthogonal to every vector of W. Okay, and we denote this orthogonal complement by W and perp. This is a notation. We call it as W perp, that symbol for perpendicular. So W perp is the orthogonal complement of W, which means it is the collection of all vectors in Rn which are orthogonal to every vector of W. So with that we have the next theorem. Let W be a subspace of Rn, then W's perp is a subspace of Rn. So you have to prove that 0 belongs to W perp. If you choose any two elements of W perp, then their linear combination is in W perp, etc., etc., which is required to prove that a given space is a subspace. That is the first part. Then B part is the only vector common to both W and W perp is 0. That is, 0 is the only vector in W intersection W perp. Third part is the orthogonal complement of W perp is W itself. That is, W perp, the whole perp is equal to W. The proof is again an exercise. It's a simple proof. Next theorem, let A be an m-by-n matrix, then null space of A and row space of A are orthogonal complements in Rn. Also, null space of A transpose and column space of A transpose are orthogonal complements in Rm. This is again left as an exercise. So we have certain remarks again. The above theorem provides a geometric link between the fundamental spaces of a matrix. So the geometry comes in terms of the dot product. Okay, so these theorems of course gives geometrical link between the fundamental spaces A, the row space of A, column space of A, null space of A, and null space of A transpose. Then another remark is you are giving, or we are given a list of equivalent statements regarding a given matrix n by n. So let A is an n by n matrix, then the following statements are equivalent. First one is A is invertible. Second statement is Ax equal to 0 has only trivial solution, which you have already proved. Then third statement is the reduced echelon form of A is In because it is invertible. Fourth statement is A is expressible as a product of elementary matrices. That is also proved. Fifth statement, Ax equal to B is consistent for every n by n matrix, n by 1 matrix B. Sixth one, Ax equal to B has exactly one solution for every n by n matrix B. Then determinant of A is different from 0. Then the column or row vectors of A are linearly independent. The column vectors are linearly independent. Similarly, the row vectors are linearly independent. Then the column or row vectors of A spans Rn. The column vector spans Rn. The row vectors also spans Rn. The column or row vectors of A forms a basis for Rn. Since they are linearly independent and spans, definitely they forms a basis for Rn. Then rank of A is equal to n. Nullity of A equal to 0. Then the orthogonal complement of the null space of A is Rn. And the orthogonal complement of the row space of A is singleton 0. And the last two equivalent statements, you just go through them and prove it. Next is overdetermined and underdetermined systems. If the linear system has more equations than the number of unknowns, then it is called an overdetermined system. And if the number of equations is fewer than the number of unknowns, then it is an underdetermined system. So note that if the number of rows is more than the number of columns denote the number of unknowns, then it is overdetermined, and if the number of rows is less than number of columns, it is underdetermined. So in an underdetermined system, so in physical examples, we have certain constraints and certain linear system of equations. So if the linear system has more constraints than the number of unknowns, it is overdetermined, and if it has fewer constraints than the number of unknowns, then it is underdetermined. So there is a theorem regarding overdetermined and underdetermined systems. Let A be an m by n matrix. If m greater than n, that means the system is overdetermined, then the linear system Ax equal to B is inconsistent for at least one vector B in Rn. So there exists at least one vector for which the overdetermined system is inconsistent. And similarly, given an underdetermined system, then for any vector in Rm, the linear system is either inconsistent or it has infinitely many solutions. So if it is underdetermined, then there are two extreme possibilities. Either it will be inconsistent, or if it is consistent, it has infinitely many solutions. So let us go through the proof. So A part. Suppose A be an m by n matrix with m greater than n. Then A has n columns and the column vectors of A is a subset of Rm. Also, dimension of Rm is m, which is greater than n, and hence the column vectors cannot span Rm because there are only n column vectors and the dimension of Rm is greater than n. So we have already studied a theorem which says that no vectors which has less number of vectors than the dimension of the space can span the space. So thus there exists at least one vector B in Rm which is not a linear combination of the column vectors of A. So since it does not span Rm, so there will be a vector which is not in the linear combination of the vectors. Thus B is not in the column space of A because it is not in the subspace spanned by the column vectors. Okay, therefore the system Ax equal to B is inconsistent because we have already studied in a theorem that Ax equal to B is consistent if and only if B is in the column space of A. That is the A part. So there is at least one B for which the system is inconsistent. Then let A be an m by n matrix with m less than n. This is the underdetermined case. for any b belongs to Rm, either Ax equal to b is consistent or it is inconsistent. So if it is consistent, then there is nothing to prove because we have proved it is consistent. So suppose it is inconsistent. Okay, then let us assume rank of A equal to R, then R is less than or equal to the minimum of m and n, and since m less than n, we have R is less than or equal to m. So R is less than or equal to m, or R is strictly less than n. Then the general solution of Ax equal to b has n minus r parameters, which we have already studied in the previous theorem. That is, the general solution has at least one parameter because n minus r is strictly greater than 0, and hence there are infinitely many solutions. So we have some examples. What can you say about the solutions of Ax equal to b of 9 equations in 6 unknowns with rank of A equal to 4? So the system, since the number of equations is more than the number of unknowns, it is overdetermined, and there is at least one b in R9 for which the system is inconsistent. Also for any b for which the system is consistent, the number of parameters in the general solution is the number of unknowns minus rank, which is equal to 6 minus 4 equal to 2. Similarly, the second one is an underdetermined system. Therefore, it is either inconsistent or has infinitely many solutions. If it is consistent, then for some b belongs to R4, the number of parameters in the general solution is number of unknowns minus rank, so that is equal to 3. So, as a last example, what conditions must be satisfied by the numbers b1, b2, b3, b4 and b5 for the following system to be consistent? So given system is x1 minus 2x2 equal to b1, x1 minus x2 equal to b2, x1 plus x2 equal to b3, x1 plus 2x2 equal to b4 and x1 plus 3x2 equal to b5. So in matrix form, if ba equal to 0, the system is consistent. Okay, so suppose there is at least one bi which is different from 0. So the cases are, it is either consistent or it is inconsistent. So we have to check when it is consistent. Then the given system in matrix form is expressed and we row reduce it. So you will get a new system. The new matrix is 1, augmented matrix is 1, 0, 2b minus 2b2 minus b1, etc. etc. So this system is consistent if and only if the rank of A equal to rank of the augmented matrix. We have already studied. So rank of A is 2. So the last 3 rows must be zeros. That means we get another system of equations b3 minus 3b2 plus 2b1 equal to 0, b4 minus 4b2 plus 3b1 equal to 0 and b5 minus 5b2 plus 4b1 equal to 0. And again solving them, we get b1 equal to 5r minus 4s, b2 equal to 4r minus 3s, b3 equal to 2r minus s, b4 equal to r and b5 equal to s. That means for these particular values of b1, b2, b3, b4 and b5, or when these equations are satisfied, the given system is consistent. So there are infinitely many choices for r and s. So you have infinitely many b1, b2, b3, b4, b5 for which the system is consistent. Thank you.